Hello everyone, and welcome to a short video for the Intro to Signal Analysis class. This video gives a short overview of sampling for sinusoidal signals to prepare you for several other examples that will be posted later. So let's go ahead and get started. So in this video we're going to focus on sampling sinusoids, although the general concepts that we'll talk about actually apply to signals that consist of sums of sinusoids. But for now we're focusing on just sinusoidal signals of the form x of t is a cosine 2 pi f naught t plus phi. So f naught is the frequency of the signal and phi is the phase. So the period of the signal, as you remember, the period t0 is just the inverse of f0. And so we see this particular version of this sine wave sketched here, and that it repeats every t0 seconds. Now the spectrum, as you know, of this sinusoidal signal contains two lines, one at minus f0 and one at plus f0. And the amplitudes associated with these lines are a over 2 e to the j phi for the positive frequency and a over 2 e to the minus j phi for the negative frequency. So this is the time domain representation of the signal, and this is the corresponding frequency domain representation of the signal. And so we're going to focus on sampling signals of this type. Okay, if we consider sampling that signal, that sinusoid x of t in the time domain, so we're taking the signal x of t in time and we run it through a little idealized box here called a continuous to discrete converter, which we abbreviate C to D. And what that C to D box will spit out is a series of samples. And I've indexed these samples on n integers. And so let me just sketch now what these samples look like on the time signal. And so what we're imagining doing is taking a sample here at 0, and a sample here, and a sample here, and here, and here, and here, and here. So we're sampling the signal such that we're taking samples so the space between these two samples here, the space between those is t sub s. Right, that's the space between this sample and this sample is t sub s, and similarly it's equal spacing all the way across. And so if we take samples like that, and now we just store them in such a way, and now we index them on n. So this is the 0th sample, the 1st, the 2nd, the 3rd, etc. So we take samples every t sub s seconds, and that gives us a signal that's sampled at a rate of f sub s, which is the sample frequency, which is 1 over t sub s, and that's in hertz. And so we might ask, well, how well does this discrete signal x of n over here actually represent what's going on with the continuous signal x of t? Well, we can see that if ts is small, if these samples are really, really close together in the time domain, then x of n is going to look a lot like x of t. But if ts is really large, we spread these samples very far apart in time, then x of n really isn't going to look very much at all like x of t, and we probably aren't going to be able to get back x of t from our samples x of n. And we have a rule for how fast we need to sample to get a good representation, and that's provided by the Sampling Theorem by Shannon and Nyquist. And they say use the sample frequency fs greater than twice the highest frequency in the signal, so greater than twice f max. In this case, if it's just a single sinusoid with a frequency f0, that says that fs should be greater than twice f0. Okay, so that's a pretty straightforward rule. We're not deriving it here, but that is discussed in the textbook and is a very common concept. So now we want to think a little bit about, we just saw what happens in the time domain when we sample a signal. Now let's see what happens in the frequency domain, or what happens to the spectrum of the signal when we take samples of it. So when we take samples in the time domain, we're getting this x of n, which is just x of t evaluated at multiples of t sub s, so n t sub s. So that, if we just plug in for our formula for x of t, we get x of n is a cosine 2 pi f naught n t sub s plus phi. Okay, and so we're doing that in the time domain. Here's the time domain signal. Here's its equivalent frequency domain representation. We run it through a C to D box. We get out this series of samples here. Now we can show, and we did in class last week, that we can show that these samples could come from a cosine with frequency f0 plus L times f sub s. So L is an integer, so it says these samples could equivalently have come with a cosine of a different frequency, a frequency that is f0 plus some multiple of the sample frequency. And what that underlying that means, it's we can kind of represent that by the fact that the spectrum now of this sampled signal x of n is periodic. Okay, so we have the spectrum of the original signal, and that I've sketched in black right here. Okay, but this signal also equivalently could come from a higher frequency signal that is up at, say, f sub s, f0 plus f sub s, and f0 minus f sub s. Or sorry, f sub s minus f0. And so that's the copy here, okay? Because these are spaced around plus and minus f0, and we can just write in where these other points are. This point, whoop, wanted to change color pen here. This edge here is at f sub s minus f0, and this point here is at f sub s plus f0. So this is the copy that we see around fs. Okay. Similarly, we have a copy around 2fs, and that's drawn in orange here. We have a copy around minus fs, that's drawn in red. And I could continue drawing copies all the way out to the left end of the spectrum going to minus infinity, and all the way out the right end of the spectrum going to positive infinity. And what this spectrum really means is, well, the samples here could come from this signal, but they could also come from a signal with a higher frequency, okay? Equivalently, there's no difference in the samples that we would get from a signal that had this higher frequency, or from this higher frequency or this lower frequency. Okay, so the basic concept that's being illustrated here is that if we sample a signal in time, effectively what's happening is that we're getting copies of that spectrum in the frequency domain, and we get, this is our original spectrum, and then we get copies of it out equally spaced, and they're centered around f sub s, 2f sub s, 3f sub s, etc. Okay, so that's what happens that's what happens in the frequency domain when we sample in the time domain. And it's a good graphical way to try and analyze sampling problems. Okay, so once we have a signal and its samples, how do we recover that signal from its samples? Well, we can imagine some sort of ideal discrete to continuous converter, and that's what's indicated in this box here. It takes a set of samples indexed on n, and it reproduces a continuous time signal that I've called xr of t. And that R is for reconstructed signal, okay? And so what's going on in the spectral domain when we do this? In the spectrum, what happens is we have this spectrum here for the sampled signal that consists of the original spectrum plus all of its copies. And what the D to C box does is the D to C box effectively just picks off the copy right around, well, it picks off this copy right around 0. Okay, so ideally what's happening is it's saying, okay, everything between minus f sub s over 2 and plus f sub s over 2 is the spectrum of the continuous time signal. So this continuous time signal is really only non-zero here between f sub s over 2 and minus f sub s over 2. Okay, so we're going to end up with our reconstructed signal that lives in this region. And there are zeros outside of this. There are no more copies over here. Okay, so this is an ideal D to C box. And if you'd like to think of it in terms of filtering, some of you have done filtering before, what it's doing is applying basically a low-pass filter that's just picking off this copy here in the low frequency band between minus fs over 2 and plus fs over 2 and gets rid of all the other copies, and that actually recreates a continuous signal. And so what comes out over here is some continuous signal. Okay, now that continuous signal, if we've sampled fast enough, so if fs is greater than twice f max, which in this case is just a single sine wave, so it's fs greater than 2f0, then xr of t is going to be equal to x of t. So we'll get back exactly what we put in to our C to D box. And that means fr is equal to f0. And what that means is when we pull off, I've kind of sketched it over here, if we pull off the frequency spectrum just between minus fs over 2 and plus fs over 2, we get back the original thing, which has a line at minus f0 and a line at plus f0. If, however, we haven't sampled fast enough, xr of t is not guaranteed to be equal to x of t, meaning fr is not going to be equal to f0, and I've illustrated what's going to happen here. If we haven't sampled fast enough, we've probably moved fs closer to the origin. And what's happened is now this copy, say this piece, has moved inside the green line, and the black line has moved outside the green line. So you're not getting the original thing. The original thing lives outside this minus fs over 2 band. And what you're getting is the piece from the little copies. So we get this edge here, or this line here, and this line here, because now they show up inside and the black lines show up outside. So that's kind of graphically what's going on there. Okay, so the first case is the case where we've sampled at a high enough frequency. We get back exactly what we put in. If we don't sample at a high enough frequency, then these copies somehow have effectively overlapped, and some of these lines have switched order, and so what we get back is something different than what we put in. So that's kind of a graphical picture of what's going on. So this is a summary of that overall picture. Sampling, we take a continuous time signal, run it through a C to D converter, and we get samples in the time domain. So we get samples at discrete points in time. And from those samples, if we want to recreate our continuous time signal, we run it back through an ideal D to C box and reconstruct a signal xr of t. So in the spectral domain, what's going on, here's our spectrum of a sine wave. And it's not periodic. Note, it just has two single lines, since all I'm sampling here is a single sine wave. So no copies here. The minute we do the sampling, now we've converted it, and we have a periodic spectrum, which means we've taken our original spectrum and we've repeated it at multiples of the sampling frequency fs. So a sampled signal has a periodic spectrum. And then if we run it through the D to C box, we come out with xr of t, which is the reconstructed signal. And so again, we'll get, if we've sampled a sine wave, we get something with just two lines in it. This is not periodic because our ideal D to C has gotten rid of the periodicity because it just picked off the copy around 0. It's not periodic. We'll get back our original signal if we sampled high enough. If we didn't, then we're not guaranteed to get back our original signal. So this is a good overall picture to keep in mind of the sampling process. We start with a continuous time signal, has a spectrum that's not periodic. Our discrete time signal here has a spectrum that's periodic. And then we reconstruct a continuous time signal that is also not periodic, and it may or may not be equal to the original, but that depends on how fast we've sampled. So that's the overview of sampling. We have one other minor issue to discuss before we finish up here. So let's make a note about some normalization. Okay, so when we take samples in the time domain, we can plot them on an axis where we're still leaving them spaced at the sample frequency. So the first sample is at 0, the second sample is at t sub s, then at 2 t sub s, 3 t sub s, etc. So that's on a regular time axis, which would say typically be plotted in seconds. And that has a frequency spectrum that looks like this, right? We have the copies in the frequency spectrum, and those copies are located every f sub s. And these three little dots here just mean that these copies repeat on out to negative infinity and positive infinity. Okay, we can also think about, well, you know, if I'm going to store this thing in a vector, store it in the computer, say store it in MATLAB, now I'm not going to store this whole time axis here necessarily, right? I'm just going to store the sample points in a vector. And so they'll be numbered, 0, 1, 2, 3, all right? So I've basically normalized the time axis. And what do I mean by that? When I say I've normalized the time axis, I've effectively said n is equal to t over t sub s, right? All I've done is taken a factor of t sub s outside of the time out of the time axis. So now it's just indexed by 0, 1, 2, 3, the integers. Okay. Well, if I normalize something in time, if I change that time axis, well, naturally you'd expect that something would also happen to the frequency axis, right? Because frequency is just how fast something repeats in the time domain. So we might naturally say, well, that kind of corresponds to a frequency axis normalization. And indeed, we can normalize the frequency axis. And what we're effectively doing is normalizing the frequency axis by dividing by f sub s. Okay. Equivalently, we could say, well, equivalently, we're also multiplying by t sub s, so that f hat is our normalized frequency axis. That's equivalent to taking f times t sub s, right? Because t sub s and f sub s are inverses of each other. And so that makes sense. We've divided the time axis by t sub s, which means we multiply the frequency axis by f sub s. And so this is our normalized frequency axis, f hat. And now, if we do that, well, now the copy that was at f sub s is just going to show up at 1, sorry. The copy that was at 0 shows up at 0. The copy at minus f sub s shows up at minus 1. So here now, the copies are at the integers, minus 2, minus 1, 0, 1, 2, etc. Occasionally, we want to write about or talk about things in terms of radian frequency, and so that's without the 2 pi pulled out. So we could define an omega hat, which is just 2 pi f hat, 2 pi f hat. And so now, if we do that, we're just multiplying f hat by 2 pi. So now the copy that was at 1 shows up at 2 pi, the copy at 0 shows up at 0, the copy at minus 1 shows up at minus 2 pi, etc. And if we think about the unit circle, when we talk about complex numbers, it sort of makes sense that we would get copies every 2 pi, because 2 pi takes us all the way around the unit circle. So a trip all the way around the unit circle, and we're back to where we started, and that is part of the reason why we have this periodicity every 2 pi when we talk about things in radian frequency. Okay, now we want to think about, well, these are just, you know, this is a copy, etc., right? And so really there's only one part of the frequency axis that's unique, and the rest of it just repeats outside of there. And so the part that's unique is the part between fs over 2 and minus fs over 2, right? Okay, so that's the only unique part of the spectrum here. And so, and everything else, we've just got an identical copy of what's here over surrounded or centered on f sub s, etc. Now, we could say, well, what is the sort of unique region in these other cases? Well, f sub s over 2 in f hat language maps to just 1/2, and minus f sub s over 2 is minus 1/2. Okay, so the unique part of the spectrum here in our normalized frequency axis is between minus 1/2 and plus 1/2, and the copies show up at integers. In our omega hat sketch, the unique part shows up between minus pi and plus pi. Okay, so we get basically a 2 pi region in here that is the unique part of it, and then it's just copies outside of that. And again, if you want to try and remember that, you can think, well, all the way around the unit circle is 2 pi, so there's really only one 2 pi region, and then we just repeat outside that. So again, the regions that we care about here, if we're plotting things in terms of f, we care about the minus fs over 2 to plus fs over 2 region. If we're plotting in terms of f hat, we care about the minus 1/2 to 1/2 region. And if we're plotting in terms of omega hat, we care about the minus pi to plus pi region. So if we know that these are all periodic, we can get away with just sketching only this other region and putting ... outside of that. But it's very helpful, particularly when doing this sketch, to actually draw all the copies out, because that's the way that you figure out where those copies go. And if you have aliasing, it allows you to see that. Okay, so that brings us to the end of our short video here. Hopefully that's given you a good introduction to sampling. And again, I'm going to post several other examples where we'll just go ahead and crunch through some problems and analyze how signals look when they're sampled and how they look when they're reconstructed. So just some brief other info. This video was made for the ECE 201 course at George Mason University in fall 2014. If you want more information about George Mason, the Volgeneau School of Engineering, or our ECE department, you can check out these websites. Thanks for watching.